Well, it's still 5 minutes. Maybe a few more. When we started having this, my microphone.
Hey, that's just a quick announcement before Professor Boser starts his lecture. So, welcome to Lecture 4 of Module 2. You probably all know that midterm scores were released yesterday, so congratulations on being done with midterm 1. Probably some of you did better than you expected. Probably some of you did worse than you expected. Some of you did exactly as you expected. Probably some of you did better than your friends in the class. Some of you did worse than some of your friends in the class. Some of you did similar to your friends in the class. I would like to encourage every single one of you to try and avoid any kind of these comparisons, because I know for a fact that every single one of you did better than if this midterm had been conducted on the first day of class. So just keep that in mind and think about how much you have learned in all of this time. That said, I know that there are people who probably feel that they wish they had done just a little bit better. And don't worry, we have a lot of resources in place for you to be able to build up and catch up on, the few problems that you might have missed on the midterm. So there's a big post on Piazza reminding you of every single office hour, every single discussion section, and the homework parties. You don't have to have questions to come to office hours. You can just come and work on your homework there. You don't have to ask questions only about what's currently happening in lecture. You can ask questions about past homeworks. You can come talk about previous exam questions. You can come and just sit there and read the notes, and if you have a question, that way there's someone right there who can answer the questions for you. So you don't need to necessarily come with a prepared question. And, of course, Professor Boser and I both have office hours in addition to all of the office hours of the TAs, so please feel free to come to any of us. We're also trying to encourage people to form study groups. I know that there's some people in the class who might feel like they're studying on their own. They don't feel entirely comfortable working in the large groups. And so there's some resources that we're posting on Piazza. So if you'd like to find study partners going forward, please use those resources. Midterm 2 and the final are, going to come up shortly. You have lots of opportunities to keep improving your performance in the class. So great job on how far you've come so far, and keep focused forward so that you can do your best in the midterms to come. With that, Let's start the lecture.
Thanks. So now... So now I'm on... this is on, yeah. Now I'm under the gun because I have to get a better mean than Professor Ranade, obviously, right? I think midterm 2 is going to be very hard. That way, you have low expectations, and then if the midterm isn't that hard, your expectations will be exceeded. Now, in the next class, I'm going to teach you psychology. Okay, with that, let's stick with circuits, nevertheless, for today at least. So we're going to wrap up the 2D touchscreen, and then we're talking a little bit more about circuits. So more insights in circuits. So let me just redraw the 2D touchscreen. This is a top view. So there are these two bands at the top and the bottom where we contact it. And because it's a 2D touchscreen, there's going to be two sheets. Both of these sheets are resistive. They have some sheet resistance or resistivity. Rho, that could be the same or it could be different for the two touchscreens. But anyways, they have some resistivity. And so the way it works is that, let's use the coordinates like everybody sort of used to for once. So the way it works is that it goes in two steps. First, we use the green sheet in order to find the X position of the finger, the touch. So I'm going to touch anywhere here, for example, at this location. I press down. That puts the green and the blue layer into contact, makes contact between them, so current can flow, or at least we can pick up the voltage. Okay, so in the first step, when I want to find the X position, I put the voltage source across the green one, and then what I'm getting is the voltage Vx is going to go from here up to the voltage source as a function of x, right? And then because we are pressing on the blue screen, the two are together, and the voltage at this point, what voltage is this? Well, that's this voltage here. That voltage appears on the blue screen, okay? On the blue sheet. Let's draw the circuit model for this. The green sheet really sets up two resistors between a voltage Vs. That's voltage Vs that we apply on this side, and a ground we apply it on the other side. Okay? So here we put ground. Okay? And then there is the red point, and we can give these resistors a name, or 1, which is the value is a function of x, or 2, and the value is a function of x, and we've calculated this before, right? Okay? So then there is the red point, and that goes into the blue sheet. And there is a resistor. The blue sheet is resistive also. And let's not even try to figure out what the resistance is. But what we want to definitely find out is here we're going to put our voltmeter. And if it works, here the voltage is Vx, and we would like that our voltmeter here displays us what voltage? Vx, right? That's the whole point. We are trying to find out Vx. Why? Well, because Vx, according to this diagram here, Vx is perfectly correlated with position x. If we know Vx, we can then also back calculate what x is the position. Okay? Does this make sense? Are you with me? Okay. So the question is, this would of course work if this resistor R3 wasn't present, if that was just a wire, right? But the resistor R3 now is present because we've decided, hey, we are cheap, we don't want to have all these extra layers, we are just going to have 2 layers, and because of that, both layers are resistive, and now we have this resistor R3 to deal with. So is this resistor R3 a problem? Well, anybody has an idea? Yes. Okay, perfect. So the answer was it's not a problem because the voltmeter is really an open circuit. So remember that a voltmeter, we use this symbol here for a voltmeter. But it's not really a circuit element. What really a voltmeter is, if we drew it as a correct circuit element, would be this open circuit. Okay? If we have a good voltmeter, that voltmeter behaves just like an open circuit. If it's ideal, it will be exactly like an open circuit. If it's a real voltmeter like the one I brought last time, then it will be very, very close to an open circuit. So once we know that it's an open circuit, then we know that the current through that open circuit, who votes for 1 amp? No, the current through an open circuit is always going to be 0, right? It doesn't matter, it's going to be 0. We can know this for sure, okay? And if the voltage through resistor R3 then is 0, what is the voltage across? The current through resistor R3 is 0, what is the voltage across R3? It's also 0 volts. Well, if there is 0 volts across that resistor R3, then the voltage at the red point and the voltage at this point here that the voltmeter actually sees are going to be exactly the same. So the presence of the blue resistor R3 doesn't mess up our measurement at all. It does not matter what it is. Okay? As long as we have a good voltmeter, that is an open circuit. Okay? All right, so that's the touch sensor. Now it works in 2 steps. We've looked at how to measure the X position. Once you're done with that, you reconfigure your circuit, you connect the source now on the blue layer, and you measure with your voltmeter on the green sheet. So the colors here simply flip, but the circuit otherwise is exactly the same. Okay. Does this make sense? Okay, so you're going to do this in the lab. Here is how it looks like. You will find that it's a little bit different. It's a little bit different in the lab. You're going to use these resistors to sort of simulate that sheet that should be resistive. Rather than having a sheet that has uniform resistivity, you're going to use discrete real resistors. You can see them here. You will solder. I think you soldered them already this week, right? So use those, and then you have various points where you can detect touch. And there's going to be all this switching stuff and the voltage measurement and so, and that's going to be done with this little board you connect them together. There's just going to be 4 wires that connect the two together, and these 4 wires, they correspond to connecting the blue and the green here, connecting those to the microcontroller, and then of course there is a program that does all the switching and all the voltage measurement and so on, and displays the result. Okay? So, you're going to do this in the lab. Okay, so in class we're going to get ready pretty soon to build version 2 of the touchscreen. Well, what's version 2? Well, you know, the world has gone from resistive touchscreens to capacitive touchscreen, whatever that is. A week from now, we will know what it is. Okay? And so in a capacitive touchscreen, for example, we don't need to press, so there is no squish or whatever, and your smartphone probably uses a capacitive touchscreen. So we really want to learn about that and how it does that. Some kind of really interesting stuff, because electronics can see stuff we can't see. And so we will do that soon. But before that, let's learn just a little bit more about circuits. So we have our weapons to analyze them. So what we're going to talk about now is equivalence. So equivalence is basically a measure where we can say whether when 2 circuits are equivalent to each other. We will define what that is. So let's start with the following circuit. We have a resistor. Let's call this resistor REQ. And we would like to draw the IV characteristic of this resistor. So over here we have I and we have V. Okay? And we would like to figure out what this IV characteristic is. Now, if you were in the lab and I gave you a resistor and you don't know the value or so, how would you do that? Any ideas? Yeah, well, you would take a supply, either a voltage supply or a current supply, for example, like this. We test. Put this across. And then you would get out your ammeter and you would measure the current that's flowing. Let's call this I test. Okay? And when you've done that, you would get, you do this for a number of values for voltage and current, you get the curve like this. Okay? We know that it's going to be a linear curve because after all, we know how resistors work. Okay? So you can do this in the lab. And of course, we could have done it also here in the here with paper. So let's actually just do that. Let's start with another circuit. This time looks like this. R1, and R2. And we want to draw now the IV characteristic of this new circuit. So here is, these are the terminals where we're interested. We want to know what's going on between these two round circle-ish terminals, okay? How are we going to do that? Well, we're going to again use a test source. Let's use a current source. For now, you can use either. Sometimes the math gets a little bit easier or harder depending on what you use. So this is I test. Okay? And then we want to also, then we're going to measure also the voltage V test between here and here. This we're going to measure. Okay. And so actually we can calculate, of course, what V test is. Well, this current I test will come out of the current source. It will see the resistor R1, and where is it going to go? Even though the current doesn't like to go into a resistor, that's the only choice, so it will go through the resistor R1, and then it will continue through resistor R2, because there is no other choice, right? It has to go into R2, and ultimately it goes back into the current source I test. So the voltage across here is going to be R1 times I test, and the voltage across here is R2 times I test, and these are just in parallel to V test, KV, something, question? It's okay? All right. So from KVL we know that V test is equal to the sum of these voltages that we just got. So that's going to be equal to R1 times I test plus R2 times I test. And I factor I test already out. Okay. And so we can say that the V test over I test is equal to R1 plus R2. And of course here I didn't do this, but we could have done also V test over I test. If we analyze this circuit, you'll find that that ratio is just Ohm's law, right, is equal to Req. Right? And so the slope of the red line. So if for some reason I had chosen the sum of R1 and R2 just being equal to R test or Req, then how would the IV diagram for R1 and R2 look like? It's the same thing. I have it already here. This is Req, and this is also equal to R1 plus R2, if I've chosen them to be equal to the sum of if I've chosen Req equal to the sum of R1 and R2. Okay. So these two circuits, they have even though one is just one resistor, and the other one is two resistors, they have exactly the same IV characteristic. Okay? And so we say that these circuits are equivalent. Equivalent Okay, so that's how we define, if you want, equivalence. Okay? So, now what this means is going to be very helpful. You will see very often. Sometimes you have circuits with many resistors, but if they're all in series like this, R1 and R2, and maybe there is an R3 also in series, we can replace all these resistors with just one of them that is equal to the value is equal to the sum of the individual resistances. Very convenient. A complicated circuit suddenly becomes a very, very simple circuit. Do this on the exam, for example. So of course, they are equivalent and in the sense that they have the same IV characteristics. They're not equivalent in the sense that if you were interested in the voltage at this node, well, that works very well in the version where I have 2 resistors, but it doesn't work so well in the version where we have only REQ. That node doesn't even appear. Right. So equivalence is very useful, but you have to be careful. Sometimes if you reduce something, make it too simple, well then the stuff you're interested in is no longer present. That's not good. All right. So, let's try another example. So the single resistor EQ we leave alone, but let's say we have a circuit that consists again of 2 resistors, or 1, and another resistor, or 2. But now these 2 resistors, they are not in series, they're in parallel. And we want to know what they are equivalent to. Okay? So again, we are going to hook up a source here. Just we go to the lab, or we can do it analytically here. We put a source here that is V test. Just VT. And then we figure out, we want to know what is I test. Okay. Well, I test is going to be equal to the current IR1 plus the current IR2. Right. This is simply Kirchhoff's current law. You know about that. If you're concerned, if you're not unsure, then you can always write a KCL equation here. Everything that leaves the node, that's IR1 plus IR2. The sum of everything that leaves the node is equal to what goes into the node. Okay? So that's KCL. We always can do that when we are not sure, but more we'll just see this stuff, right? And so what is IR1? Well, now we can, IT is going to be equal to IR1. Well, IR1 is going to be VT. Yeah, the voltage here is going to be V test. The bubbles, they are just a funny way to indicate where we connect to a circuit. That's not a circuit element. So this voltage V test also appears here, and the same voltage V test appears here. Okay? So the voltage across resistor R1 is V test, and therefore the current is equal to V test divided by R1, Ohm's law, and ditto over R2. So the equivalent circuit, so now let's divide out I test over V test. Well, that is just equal. So over here we wrote V test over I test is equal to R equal, right? Or EQ. Well, then here we have I test over V test, so it's just the inverse. R EQ equals to 1 over R1 plus 1 over R2. So, again, if, and of course we can solve this, we can say that REQ is equal to R1 times R2 over R1 plus R2. And this is a lot to write, and because we are engineers, we are efficient, we don't want to write more than necessary, we simply often write R1 parallel R2. You can see that R1 and R2 are in parallel, and we simply use this parallel symbol. So when you see this parallel symbol and you want to know what really the value is, well, you have to go and use this expression up here. Okay? So now we have two rules that when we have resistors in series over here. Then the resistances just add, and if the resistors are in parallel, well, then it's the reciprocals of the resistances that adds. Okay. So let's look at a little example how we can use this productively. So let's say we had a circuit like this. My resistors get fancier and fancier, okay? So as a resistor R1, R2, R3, R4, okay? So we have 4 resistors here, a terribly complicated circuit. So, question, could we replace this circuit with just one equivalent resistor? Okay, let's try it. Actually, why don't you try it? You spend a minute or so, and then we will do it together, okay? You can tell me what you got, and I'll think about it too. Who has the solution already? More time? Oh, some folks. Okay, let's do this together. If somebody wants to, yeah, I think you back there. Oh wow, impressive! Yeah, I think that's correct. I think it was R1 times R2 plus R3 times R4 divided by R1 plus R2 plus R3 plus R4. So, anyways, let's do this. Let's do this together, and let's do it in some steps. Okay. So, what we would like to know? We treat this whole thing as sort of a black box, if you want, and we would like to know how does this black box behave between the two round circles. Okay, so we can do this in steps. So the first step, 1, is to replace all the resistors that are in series with equivalent resistors. So we have a new circuit that is equivalent to the original one. But instead of having R1 and R2 in series, it has a new resistor here that is the equivalent to R1 and R2 in series. And over here there are R3 and R4 in series also. There also we replace those two resistors with equivalent resistors. So what is the value of the resistor on the left side? Okay, this is one R1 plus R2. And over here we have R3 plus R4. Okay? And then you do a second step where we are going to replace these now with the parallel resistors with the new resistor. And what is the value of this? We call this one now the equivalent resistor. What is the value of it? Well, it's going to be R1 plus R2 in parallel with R3 plus R4. Okay? That's That's what we get there. And now, of course, we can easily, this parallel business, or EQ is equal to or 1 plus or 2 times or 3 plus or 4 over the sum of all of these. Okay, so this is our example. So without doing any KVL and KCL and without even ripping out test sources and voltmeters and ammeters and so on, just by knowing about series, resistors in series and resistors in parallel and how they behave or how the equivalent circuit looks like, well, we can reduce complicated circuits like this one quite easily, and I come up with some more complicated one for the midterm, or at least for one of the homeworks. Okay, so that's just mechanical. A computer could do it, so we can do also. Okay, we'll have a lot more circuit stuff to do, but before we get there, let's give ourselves a little bit of a treat. Okay, so you know this, who knows Fruity Fred? Yeah, okay. You know, I called him up and I asked him about his stuff, and so he was very nice. He showed me his scale, and so we'll talk about how it works. So this is a rubber band. If I pull on it, it gets longer and it gets narrower, right? Imagine this was a resistor. Would the resistance change? Would it go up? Would it go down? When I pull on it, it will go up, right? If I somehow manage to, that doesn't work very well, compress it, probably the resistance actually would go down. Okay, so we can do this. We can use this to sense forces. So this thing here is called a load cell. And this is what is in your kitchen scale. So when you're at home, your mother doesn't look, just pick it and take it apart and you'll find something like this inside. The bathroom scale may be a better candidate even. Okay, so there are 4 wires coming off this. And there is some stuff here, some isolating material so you can't see it. But underneath these areas there are actually 4 resistors. There are exactly 4 resistors like are shown here, okay? And then there is a hole here in the middle so that it's a little bit softer material, it's aluminum, is a little bit softer here. So if I apply a force, you cannot see it, but it bends a little bit, right? And that means that the resistors at the top here, on this side, they're going to get a little bit longer. And the resistors at the bottom side over here, they get a little bit shorter, right? You cannot see it, but the resistance changes a little bit. If you have a good meter that can sense these resistances, you ought to be able to find that force, right? The effect of that force. Okay? So that's what Fruity Fred did. You see the same piece here, the same load cell, the resistors, the 4 wires, and then it's hooked up to this thing here is a microcontroller. It's actually a little ARM CPU. The same computer that's in your smartphone, just, it runs a little bit slower, uses a little bit less power and has less memory and so on. But other than that, it's exactly the same. It's programmed in Python and, well, it can run all sorts of programs. Let's see if we can. So this is just a battery that I plugged in. Okay. And now can you see? Well, of course you can. Well, let me see if this Zoom business works here. Oh, yeah, you can sort of see. What it says there is weight, and it says minus 34, 38 grams. So the first thing we need to do is we need to zero out the scale, and we can press this little button, and now it's zeroed out. Like your mother's kitchen scale has a button like that too. Then here, I have a set of weights, okay? This one says 200 grams, okay? And I put it here on top of this aluminum bar. And what does it say there? 199 or 200. Hey, make up your mind. No two answers. Doesn't get an A. Or you can take this one here. It says 500 grams. Oh, works too. Or you can even do, this one says 100. What happens if I put both? Okay, so it's a little bit off, but anyways. Okay, so I wanted to, I just wanted to show you this for once. Resistors, they're sort of the simplest circuit element. That's why we start with resistors in this course. But they're actually really useful. You can make actual practical stuff. And the other point that I'm trying to make is that we are an EECS department. And the degree you get, at least if you're in the EECS side, is an EECS degree, right? So the point of this is that we have few courses that really mix the circuits and systems and the computer and programming, all of it together. But here it comes together, right? And in the lab, you're going to use both. In this course, we're not going to focus on programming, right? We're not going to teach programming. You have lots of courses on that already. But in the end, everything comes together. It's the key thing that we need to know both. We need to be both computer scientists, and we need to know how to program, and we need to know how to connect to computers, and we need to know circuits, and we need to know system theory so that we can figure out what these circuits can do, so we can design more complex stuff than just the kitchen scale. But it's a start. So I will bring this to the homework party, so we can look at it. You can look at it and see it more. I will also post the Python code that powers this little scale. I will post it on the course website. Let me just say, and it says that also, this is not really sort of part of the course. It's not going to be on the exam, okay? We are not going to have Python questions or stuff like that on the exam. But I thought it would be useful for you to see an example that once you mix all of this stuff together, it gets pretty exciting very quick. And that maybe in your next project is one of these quadcopters that runs upside down and I don't know what. Okay, so with that, before. There is one more thing that I wanted to point out here because it leads me to the next thing we want to do. And that is, here are the 4 resistors over here, and we can't quite see them, but we could measure it, right, sort of this black box approach. And over here is the computer with the display on top. But there is another black thingy here. That's kind of interesting. And so let's talk about what that black thing is. Well, that black thing is actually called an amplifier. And why do we need it? Well, what the amplifier does is it makes small signals bigger. So here we have a voltage V in, and then a voltage V out. And let's say the voltage here goes up to 0.1 volts. Ooh, sorry about that. Thanks. Okay? So 0.1 volts, there would be minus 0.1 volts over here. So that's the input voltage. But let's say, and actually that's the case, the microcontroller inside here, it cannot deal with really small voltages. You know, this thing here, when I bend it, it bends just a little bit. So the resistance changed just a very little bit. So I get only a few millivolts out of my circuit. Okay? So that's the horizontal axis V in. Well, the microcontroller, it needs volts, okay? It can resolve then, it can measure them accurately, but the signal needs to be reasonably big. So we need something, some gizmo, that takes a small signal and makes it bigger. Okay? And that thing is called an amplifier, and it has a characteristic like this, where let's say that this is 1 volt here, and this would be minus 1 volt. Then the characteristic, this is now a VV characteristic of the amplifier, for example, would be like this. when we put in, let's say, 0.1 volts, we get out 1 volt, so that would be the gain of this amplifier is 10. Of course, you could have another amplifier that has a gain of 100 or any number that you want. Okay? So amplifiers, they're very, very important. For example, your phone, your smartphone, on the antenna, it gets microvolts. If you hook that up to a speaker, do you know what you hear? Nothing. It will be totally quiet. You can't hear a thing. So in between that antenna and those microvolts and the speaker that needs volts, there is an amplifier, plus some other stuff, radio and so on. Okay, so what are these? Yes. So the question is there a large loss in the quality of the signal in the amplifier? So that's certainly possible, and this is something that as engineers we have to deal with a lot. If you need to amplify a signal of 0.1 volt to 1 volt or so, that's not so difficult. But if you have a signal that is a very, very weak signal on the antenna of your phone, then you can have an amplifier that has large gain. Now it's a big signal, but as you sort of suspect, it also messes up the signal. And so that's why when we listen to a phone conversation, especially on old phones before they did all sorts of digital tricking, then if the connection is far away, or let's say on a radio, so maybe you have that, an AM radio far away, then the quality starts dropping. Those are very interesting topics, and they also tell us how much power we need or what we can do. And so anyways, this gets really exciting. I have a long list of classes that I can recommend you take to learn about this, but maybe it's another thing that I will come to talk about in the office hours. Okay? So, but let's stick for now just with amplifiers. And we can, of course, have a symbol for this amplifier. So the amplifier would have an input where we apply the voltage V in. And it has an output where we apply the voltage V out. And V out is equal to some gain AV, that is property of this amplifier, times V in. Okay? So this is an amplifier. And this particular amplifier is called voltage controlled voltage source. Well, why is it called that way? Well, it's called that way because the input's a voltage and the output is a voltage also. So it's both something that uses a voltage to control a source that also is a voltage. So let me write this maybe down. Voltage So that's what we have. That's our amplifier. For now, we treat this just as a magic black box, just like it is here. There's some magic black box, this one here, and it can do this stuff. Just in about a week or a little bit, 10 days or so, we will start looking into how to build these things ourselves, okay? But before we do that, let me ask you a question. Could you think of other amplifiers, and let's try to stick with electricity, other amplifiers that are not voltage-controlled voltage sources, but maybe something else controlling something other? Electrical. Current, huh? Current. So what about, could we make also how about a current controlled? Could we make a current controlled voltage source? How would that look like? Well, in that case, we want to figure out what the current of is between our control terminals. However, would we do this if this was in the lab? We have these two terminals. These are the control terminals for our amplifier. We want to know what current is flowing between them. How would we do it in the lab? Well, we would whip out our ammeter, right? But what is our ammeter really if it's a good ammeter? Is it an open circuit? No, what other? It's a short circuit, right? So this is our ammeter, and it measures the current I in. Okay? And then the output, well, that's a voltage source apparently. I need to change the zoom. That's the problem. Okay, too much technology for me. I'm simple farmer. So V out. V out is equal to some resistance, some gain resistance times I in. Yeah? Sometimes you need this one. Sometimes it's a current. So there are some sensors that output the current. For example, if you want to sense how much light you get, use a thingy called a photodiode, and it puts out a current that is proportional to the number of photons getting to your sensor. Then you want to measure that with your microcontroller. Well, you put it into an amplifier like this, a current-controlled voltage source. It spits out a voltage, and the microcontroller can convert that, and you can write fancy programs and sell them on Amazon or whatever. Okay, so are there other ones? Well, it's the current-controlled voltage source. Who can think of another amplifier? Nobody? I probably don't see. Yes, back there. Okay. Voltage controlled current. Well, current source. Voltage controlled current source. So that would be another one. So then voltage controlled, well, do I need to put a short between my input terminals? No, because we are sampling V in. And the output is a current source. Voila. And I out is equal to V in times, what's the unit of this thing? Through some, divided by some gain resistance, right? Otherwise the units wouldn't work out. Okay? One more. Voltage controlled current source. Anybody can think of another one? Yep. So the last, well, I shouldn't have said that. So there's the current controlled current source. Okay, so you know the fancy nomenclature, but the code is pretty simple. If you understand the code, it's easy to remember these things. Okay, so that's going to be looks like this. Picks up a current I in, and it outputs a current I out. I out equals some gain, some current gain, times I in. Okay. Those are 4 different ones. Okay. And so is there a 5th one? Not really. I mean, we possibly a power amplifier or so, but let's not get there. So there are 4 versions, 4 combinations. Simply you can fill that in at the complete table. Current in, voltage in, current out, voltage out, and all the combinations. Okay. So now we see that amplifiers gets a bit complicated, right? There's 4 different ones, at least 4 different ones, and of course they can have all sorts of different gains. Now imagine if you were a vendor and you had to stock all these different amplifiers, 4 different kinds, and then all different gains for all these different amplifiers. It would be you would have a huge stock room, and the customer will ask for one, and he wants a different gain, and you need to make that one. It's going to be pretty unwieldy. So for now, we will just sort of assume that stock room exists. But later, we're going to find out that there is one component that we'll have to learn about, and out of this component, we can make all of this stuff. That's what circuit design is about. Okay? So, we just have enough time to introduce the next topic. And the next topic is called superposition. Okay, so when we do node voltage analysis, then we find the node voltages, Vn, these are our unknowns, and we put them in a vector, and we find a matrix, Y, so this is a matrix, Y, that describes our circuit. Right, out of the node voltage analysis, we figure out that matrix, and this then is equal to another vector. Sources. These are all the constant sources. This is equal. Okay, so that's always the form that we get if you look at your homework or the example that's on the website or so. You do node voltage analysis. By the time you have it in matrix form, you always have a matrix here there that depends on the topology of the circuit. It also captures the value of elements like resistors or possibly the gains of these controlled sources. Then this is the stuff that you want to know. Of course, we have that vector. And finally, on the right side, you'll find that is populated with the sources, basically the inputs or so, the driving things of your circuit. It's always going to be of that form. Okay? And now let's multiply this on both sides with Y inverse. So we multiply this with Y inverse. So then what do we get? Well, Y inverse times Y. That is going to be unity, so we don't need this anymore. Vn is equal to Y inverse times okay. This is trivial, right? I mean, basically, what I did, maybe, just make sure. Normally, when you have a system, a linear system of equations that you want to solve with Gaussian eliminations or whatever, this one is called B, right? B, right? What you can do, of course, is you can multiply with A inverse is equal A inverse times B. You look puzzled. This is from module 1, right? Totally from module 1. And then I'm not using Gaussian elimination. I use Gaussian elimination perhaps to compute A inverse. I multiply A inverse into A. That gives me identity. So identity doesn't, multiplying with 1 is equal to A inverse times B. Okay? So A inverse is known. We figured it out from, here I called it Y inverse for some reason. And the B's, that's known. Well, these are all of our constant sources, like Vs and Is and so on. Right? And Vn, well, these are the unknowns. These are the node voltages that you're supposed to find. That's why we do this node voltage analysis in the first place. Okay. That make sense? Yes. The components of the first equations. Could I explain the components of the first equation? What is this? What is y? So I don't have it here, but if you go to the node voltage analysis handout, you do all these steps, right? At one step, then it says, okay, now let's put it all, fill it all into a matrix. You get a bunch of linear equations, and then it says, let's put it all into a matrix. Well, you get a matrix, I think in that handout, I call it y times the node voltages that you want to find is equal to some constant stuff that you figured out. Okay? Yeah. Sorry about that. To make this clear, but thanks for the question. So, everybody on board. By the way, sometimes I do not see hands. I'm not used to such huge classrooms. If you have a question, I don't see your hand, please just holler, okay? I cannot get new eyes, but you can holler. Okay, so, all right, so why did you do this? Well, because of a little bit of insight that we can gain from this equation. So, apparently the node voltages in any circuit, at least a linear circuit, they're equal to the sources that are driving that circuit, so Vs, Is, or whatever we may have there, times some matrix that we can calculate using node voltage analysis, okay? But this is a linear equation, so what this linear equation tells us is that the value of the node voltage is simply a linear combination, a linear weighting of the sources in our circuit. You have a question, or? Yeah. I didn't. Oh, y may not have an inverse, but let's not. In interesting circuits, it will have an inverse. Okay. In interesting circuits where we can find the node voltages, then it will also have an inverse. Okay. That's a good point. Mathematically, I'm not as rigorous as in Module 1. I forgot how to do that stuff. Okay. Any other questions? Okay. So y has an inverse. And then the node voltages in a circuit, they're simply going to be equal to weighted sums of the driving sources, okay, of the inputs. Well, now I have an idea. Suppose we wanted to make our life a little bit easier. Instead of let's say we have a circuit with lots of sources or so. Instead of analyzing this complicated circuit, which has lots of sources driving it, it would be kind of neat if we could solve a circuit with only one source, right? That would make it easier. In fact, let me draw an example. Makes that maybe more concrete. So, suppose we had a very complicated circuit like this one. The voltage V1, and the voltage plus minus V2, and they're both grounded. So by the way, somebody asked a question about that. When I draw a ground symbol and then another ground symbol anywhere else in the circuit, it's implicitly that these two are connected. I don't need to draw the connection, which is great because otherwise our circuit diagrams just get too messy, right, with all these wires. Okay, so anyways, we have this circuit, R1, R2, and we have a node voltage Vn here in the middle. We would like to know what this is. Okay? So, we could solve this, of course, with node voltage analysis or whatever we like. That's possible, but let's see if there isn't an easier way to get at what Vn is. Well, again, this page here, the one on the right side, tells us that Vn, it's a node voltage, one of those guys here, there's only one in this circuit that we're interested in, is equal to a linear combination of the voltage sources. So it's a linear combination of V1 plus another linear combination of V2. Okay? So let's try to do the following. Let's solve the circuit in several steps where okay, so we zero out all the sources except one. Now, this weighted sum here looks a lot simpler, right? And of course, it misses a lot of terms for all the other sources. Right? But then, afterwards, then we pick another source. We zero all the sources except now one, but a different one, right? And do that until we have considered all sources, until okay. So let's do this. Maybe it gets a little bit more obvious if we actually do this. So what does this say? Well, we look at all the sources. Well, there are sources V1 and V2 here, and we're going to zero them except for one of them. Which one do you want to zero out? V1. Okay, we'll zero out V1. So step one. What does it mean, zero out V1? Well, it means that we set V1 equal to 0. So let's redraw the circuit, but this time knowing that V1 is equal to 0. So we still have our two resistors. Vn here. But now, V1 equal to 0, what's the simplest circuit element that I can put in my diagram to represent the fact that V1 happens to be 0? It's just a wire, it's a short circuit, right? This is our new V1. The voltage across V1 is 0, and the voltage in a wire sure is 0. Okay, so now I can find Vn. Let's call it Vn1 is equal to, anybody recognizes this circuit of the two resistors and the voltage source? It's a voltage divider. It's sort of standing a little bit on the side, but it's a voltage divider. So this voltage is equal to V2 times R1 over R1 plus R2. By the way, I'll give you a little trick how to figure out which one's on top. Right? There is always, is it R1 or is it R2 that is on top? Well, we want this voltage here, Vn, is really the voltage between Vn and ground, right? It's this voltage is really Vn, okay? We are in, so Vn1 actually, Vn1. Right? So we are interested in this voltage. Well, the resistor that appears here is always the resistor across which we want to know the voltage. Okay? So that's how you know. Oh, how you can know. Okay, so we zeroed V1, so now we are going to zero out V2, right? We redo the circuit. R1, R2, Vn2, and this one now is just a short circuit. Same deal as before, Vn2 is equal. Now Vn2 is really the voltage across resistor R2. That's Vn2. So now it's again, of course, a voltage divider, V1 times, well, it's the voltage across Vn2, so the voltage Vn2, that's the voltage across resistor R2, so R2 now this time comes out at the top over R1 plus R2. What did I do wrong? Okay, no, I did nothing wrong. So now, step 3, well, what is Vn really? Well, Vn is, if we go back here, Vn is the linear combination of all these the contributions from every individual source. So we simply have to add up the Vn1 plus Vn2. Okay? Just add those together, and that's going to be equal to V1 times R2 plus V2 times R1 over R1 plus R2. Voila. Okay? Now, if you prefer, if you don't like this trick with superposition, you can also do it. With node voltage analysis. Or if you doubt whether the result is correct, well, you can do node voltage analysis and see whether you get the same thing. But was this simpler? Well, certainly, if we had lots of sources, can get quite a bit simpler. And actually, we're not going to talk about this in this course, but in 16B, this idea of linear superposition is extremely profound, because think about the following: when you analyze a circuit, you can test a circuit also. You can test it only with a finite number of possible signals. But then you go and sell this. The user is going to use other new signals. How are you going to make sure that the circuit can deal correctly with all these different signals? So what we do is we use linear superposition, and we come up with just a very small set of fundamental signals that when we add them together, we can represent all the possible signals. Very clever. So we are not going to get there yet in 16A, but we sort of laid now the groundwork that we can move to that very powerful approach in 16B. Okay, let me see if we have a... Yeah, let's make I still have 1 minute. So let's make another little example. So IS or S or VS. Okay. And I'm interested in this voltage here, Vn. So this is another example too. Okay. So so it's again 2 steps. We have to pick one source. We have 2. How many sources do we have? Well, we have IS and VS in this circuit, right? We pick one and we zero it out. Which one do you want to zero out? Let's zero out the current source. IS equals 0. Okay? So now I need to redraw my circuit, but for IS equal to 0. What's the equivalent circuit for that? What's the equivalent? I have a current source. The value of the current 0. What's the simplest way simplest circuit element I can? Open circuit, precisely. Thank you. Okay, so my circuit now is like this, or S, or V, and Vs, and here we have Vn1, Vn1. Well, I should let you do this. It's going to be equal to Vs times, again, is it going to be Rs or Rv in the denominator? It's going to be Rs, right? Because Vn1, well, I needed to put the ground there. Vn1 is really across Rs, not Rv, so it's going to be Rs over Rs plus Rv. Okay? And then, running out of paper. Then we have the second step. We have, this time we leave the current source in place. Or S, or V. Oh, nasty. Look at this. The current can flow into Rs and Rv. It's 2 on, and we want to know this voltage here, Vn2. How could you do this without doing complicated calculations? Yes. Yep. So the question is, hey, when you zero out the voltage source, you get a short circuit. Well, what does it mean, zeroing out the voltage source? It says that the voltage is supposed to be 0. If the voltage between 2 points, let's say this point and this point here, is supposed to be 0, well, it's the same as there is a wire in between there, right? Because a wire makes sure that the voltage between the 2 points it's connected to is always 0. It runs whatever current is required to make the voltage 0. So a wire is just a very simple way of saying, hey, I have a voltage source with value 0. Yeah. I guess that would be something, you know it now. On the midterm, I could make it seemingly very hard, right? I put 20 elements there, but most of them are just voltage sources and their voltage is 0. Yeah, you replace them immediately, all of them, with just wires, and your circuit gets much simpler, and you can solve it, and you get a good grade, good score. That's what I'm after. Okay, and the current source, well, what does the current source say? Well, it says, if I'm a 1 milliamp current source, 1 milliamp shall flow through this path. Okay, shall flow through me. But if I'm a current source that flows 0 current, means no current can flow. That's like there is no wire, no nothing there, so I can replace it with, just that. Nothing or an open circuit, we usually call it. Okay? So, does this answer your question? So now here, we have these 2 resistors. It's a little bit nasty. It would be nice if we had only 1 resistor. Does anybody have an idea how we can replace these 2 resistors with just 1? Yes? Exactly, they're in parallel. This really is RV in parallel to RS, and from that you get Vn2. Vn2, and I'll let you add Vn1 and Vn2, and then you have the result for this problem. Okay? See you Tuesday. All right. Thank you. So, for the homework and also to see this, I'll see you in Wozniak Lounge at the homework party, okay?
Here you wrote I out equals Gi times In. What is G?
Well, that's the gain, right? It's how much gain you want. That's a design parameter. Like, I give you a resistor, and what's the resistance? Well, you choose whatever you need in your circuit.
Okay. Thank you.
I just wanted to make sure, so when we're zeroing out current, we don't want any current in that branch, so you're making it open so no current can flow. Is that
Yeah, exactly. Yeah, if this IS is equal to 0, that means no current can flow here. That means
but
I have nothing
zero
there.
Voltage, we want the change in voltage to 0, so you just put a wire because then it makes
Yeah.
it 1.
Yeah.
Okay.
Perfect.
Right. Thank you.
Yeah.
I just wanted to make sure.
Sure.
Yeah, Professor. So if I like switch, I change here to the voltage, and here is current. So then I assume the voltage source is 0. So then I can like to change it to a wire here.
Yes. Then it would be.
And if here is current source, so here will be like so. This resistor is gone.
Yeah, the resistor may not have. I mean, it will dissipate power, but otherwise it will not have any influence on the end.
Okay. Got it. Thanks.
You talked about like the trick to kind of like put which one is on the top. I couldn't really follow it.
One second. I want to get rid of this microphone, otherwise.